Okay, so here's what we were talking about. Got through a lot of the circuit basics last time. We talked about Ohm's law, talked about the power dissipation, have three different forms of the power law. We'll see why it's nice to have three different forms of it today. Even went so far as to take a 12-volt battery, so 12-volt EMF. We, in turn, attached two different resistors to it, 2 ohms and 1 ohms. And we used Ohm's law and the power law to calculate what's the current that flows and what's the power dissipated in each one. And we found, of course, in this case, since the resistor is smaller, we found that the current flows a lot more current goes through because the obstruction isn't as big. And we found that more power is dissipated as well. And the reason why I, of course, am putting those for reference is because, as I mentioned at the end of last time, I'm going to take these exact same components, same battery, same two resistors, but now instead of hooking them up in turn, I'm going to hook them up together. So let's do the series circuit. So we'll have our 12-volt battery, and we'll hook it up with a 2 ohm and then a 1 ohm resistor. So I'll call this, I guess I should probably number them in the order because it's going to get confusing if R1 is 2 ohms and R2 is 1 ohm. So let me put them like this. Sorry. I'll put small resistor first, big resistor second. R1 is 1 ohm and R2 is 2 ohm. And it's just nice for visualization purposes to kind of draw the resistors bigger or smaller. That's something I'm doing just, it's not very common, so don't expect that in when you look at a normal diagram. You just have to look at the numerical label because it won't be like drawn in this way. And what I want to do is ask the same questions, more or less, what we asked here. What's the current flowing through each resistor? What's the voltage drop across each one? And what's the power dissipated? And I guess let me make sure to just, because I have limited board space here, let me actually try to cleave off here. Let me try to save as much room as I can. To start developing kind of a master chart, series and parallel. Parallel is the next kind, so we'll compare and contrast here our findings and kind of save up a kind of a store of knowledge that we can apply. Some of this will also be on a summary sheet that I'll post for you on circuits. Part of it will not be relevant for homework 3 and exam 1, but it will, after we finish homework 3 and exam 1, we'll continue on with doing circuits labs, circuits homework, and so I have put a bunch of circuit stuff on the same summary sheet, so it's kind of awkward. I know that this summary sheet that I'm going to post for you has some stuff on it that's on the exam 1 and some stuff that's not, so you're going to have to kind of cleave off what is relevant and what's not. So let's go through first and knock this out. First of all, in terms of current, right? Remember, current is the flow of charge. Now there are no forks in this road, okay? There is only one path. You can go through this one, and then you can't just stop here and hang out. You have to continue going through here. There's no other options. And so one of the first things that I want to point out is that the current is the same in series. So when you go, whatever charge per time goes through one has to continue through to the other. So the current is the same for each resistor in a series. So it makes perfect sense if you think of it in terms of like you have one river, right? There's no forks or anywhere where the water goes, okay? And you have one bridge and a certain amount of water goes underneath it. You have another bridge downstream, the same amount of water goes underneath. It may be harder to believe when we're talking about circuits, but there's an important thing I want to introduce to you about the nature of current flow that may not be obvious. Okay? So you might say, well, doesn't the current rush through this here, this easy resistor, and then when it encounters this big obstruction, maybe it pulls up or something. So maybe the same amount of coulombs per second that go through here don't pass through here. But here's the thing. The entire system is already filled with charge carriers, okay? Remember, this is all, there's electrons that are mobile in this entire thing. And so we have to kind of think of it, I guess I'll draw it separately so I don't mess up my main diagram. We have to think of it that the entire system is already filled with charge carriers. Like that. And when you connect the battery, the message of the fact that there's now a motivation for them to move kicks in, okay? It's like everybody's waiting in line, right? There's a huge long line, like American Idol tryouts or something. And suddenly the word travels very quickly that they've opened the doors and everybody starts moving, okay? So the thing is that the amount of resistance that is in the entire pathway is already known. And they will all start moving in accordance to how much resistance is in the entire path, okay? So it's not going to be spotty like I know sometimes like when you're waiting at a stoplight or something and there's kind of these patchy spots, right, between cars because some people go right away and other people just sit there and there's a gap that opens up and eventually if they wait too long you honk at them and they go, right? Okay, that's not what happens in electrical flow. In electrical flow, this resistance in the entire path is sensed immediately. If there's more resistance in the path, then the current will be slower or less. If there's less resistance in the entire system, there'll be more current, but it's all coordinated, okay? So that's why the current is the same in series. Because the current will start moving, having a certain sensed the amount of resistance that's in the entire system, and will move accordingly. If you need further evidence, think of it like this. When you flip a light switch, if I flip that light switch over there, the light would turn on or off immediately, right? So it may surprise you that the actual electron that passes through the light switch, when I flip the light switch, takes several minutes to get to that light bulb. The actual motion of charge carriers is actually fairly slow. But there is already an electron right in the light fixture that hears the message, oh, we're doing something now, okay? So the message of what's going on, the communication between these guys is basically almost instantaneous, even though the motion of the individual charge carriers can be quite slow. So that's the thing you have to understand. Kind of a way to think of it is it's like a pipe that's already filled with water. It doesn't take time to fill and then do its thing. It's already full, so to speak, okay? So the current that will get established is in fact going to be determined by all the resistance in the path. And as you can probably imagine, if the current is, if you have to go through a 1 ohm and then a 2 ohm restriction, basically that's like a 3 ohm restriction, right? So one of the things we can do in series, we can compute what's called an equivalent resistance. That's equivalent or total resistance of the entire circuit. And when you're doing it in series, you just add the resistors. That's all there is to it. So in this case, we have a 3 ohm resistance. The entire resistance of the circuit is 3 ohms, and that is going to inform how much current is flowing through the entire system. One of the ways to kind of think of the equivalent resistance is this. It's like imagining the entire resistance of the circuit is kind of like summarized into one, right? So we have this battery, we're going to connect it across this much total resistance, and that's going to inform the current flow. We can actually apply Ohm's law to this, so let's try it. Here's Ohm's law. So of course, if we're visualizing it as one resistor, it's just like what we were doing before. So we have that the entire voltage drop from top to bottom, all the way, the whole journey is, of course, provided by the battery. That sets the endpoints of the journey, what's the voltage difference you have to travel between. This will be the total current, and the total current will be determined by the equivalent resistance. So we can solve here for I total. I total will be the battery voltage divided by the equivalent resistance. In this case, we have 12 volts of motivation to go through this obstruction. The obstruction is 3 ohms of difficulty, and so we get 4 amps. So 4 amps, or 4 coulombs per second, flows through this system. And remember, because there's no forks in the road, the total current is one and the same through every element. So 4 amps courses through both. What do you notice about that current compared to when they were connected individually? This was 6 amps connected alone. This was 12 amps. That is less, right? Why? More resistance in the way, right? That's all there is to it. So that's what you often find in series circuits. Because you're putting a bunch of obstructions in a row, it creates this one big obstruction, and the current flow, while constant across, or the current, while it's the same in each element, right? Same in each resistor, it's not the same current as it would be if you connected them alone, right? It's usually much less. Question?
So then when you had the light set up, you had one that was bright and one that was dim.
Right, so we're working up to that.
Okay.
Right, this is just current. We can't observe current with the naked eye. We can observe power, so we'll have to work up to that.
Okay.
Let me save a blank row here. And let me say a brief few words, or I guess let me summarize that resistance rule. If you want to add resistors in series, you just add the values. Do you guys know the summation symbol? It means add stuff. Okay, so sum over n, right? And of course, if this goes perhaps without saying, but of course the equivalent resistance is going to be greater than any individual one, right? Of course, when you're adding a string of positive numbers, the result is going to be bigger than any one number in the sum. That may seem obvious, but it's nice to compare and contrast with parallel. We're going to find that there's kind of a similar sort of rule. Oh, and I guess the other thing I can say is if you happen to have a bunch of resistors that had the same value, let's say each of them had a value R, obviously these two are different, but if, let's say you had a bunch of resistors of the same value, then of course all you would do is you'd multiply by the number you have, right? So if you have 10 1 ohm resistors, you get 10 ohms, right? If you had 10 2 ohm resistors, it'd be 20 ohms, right? Again, this all may seem kind of obvious, but I'm writing it in this way so that when we get to parallel, we'll have these to refer to. Okay, so that's a little bit about, we found the current, we found the equivalent resistance, and now we are going to go to voltage. So let's go to voltage and then to power. And then we'll set it up, and we'll take a look and see if it behaves as I've claimed. Let me clear a little space, I suppose. I'll copy my result for the current. So current, I1 equals I2 is 4 amps. I'll copy my equivalent resistance is 3 ohms, and then I'll save a little space for myself to go and explore the voltage drops. Now this is a system in which you've got actually 3 different equipotential regions. So this here, this is the highest voltage in the system, right? It's the higher voltage terminal of the battery, and any contiguous piece of wire that you connect to it simply just extends that plateau. I'm going to label that, I guess, A. That's the highest voltage. And then, of course, I have my lowest voltage, That's the other terminal of the battery. So this is all one big equipotential. I'll label that C, I suppose. But I also have a middle region. So the middle region is right here. So that, remember, that's a piece of conductor, so that's an equipotential, so it's a middle step. Now, how do I know that that's the middle step? How do I know that B is going to be lower than A and higher than C? The reason is because of the current flow. Remember, current flows to lower voltage, right? Current is positive charges like lower voltage, right? A charge will never do anything except if you reward it. So if current is going to flow from A to B, B has to be lower voltage than A. But if B was the lowest voltage, why would anything go anywhere else? B also has to be higher voltage than C, because current wouldn't continue through from B to C if C wasn't even lower voltage than B. So there's a middle step. The way I like to draw this is, I call it like a voltage schematic or like a voltage waterfall. Okay? So when I draw these, so voltage, schematic, something's going on with my spelling here. Hold on. Schematic or waterfall. So I imagine the journey of the charges going from the highest voltage down to the lowest voltage, and along the way they have a stop. So in these drawings that I use to kind of visualize the circuit, when something is higher on the board, it's a higher voltage. So here's what I'm going to draw. Let's draw it like this. So I'm kind of imagining this as a two-step drop. So charges start at the A, the highest voltage. They drop down through resistor 1 to that middle step, step B, and then they drop through resistor 2 down to the final bottom, the lowest voltage C, and then, I guess this is, we don't need to worry about this too much yet, but I do want to point out that what the battery does, the battery basically functions like a pump, okay? It recycles the charges by bringing them back up to a higher voltage, okay? So the waterfall is not just a good analogy, it's a great analogy, okay? The battery is like a pump, and then the two tiers of this two-stepped waterfall are the voltage drops that you have across the resistors, okay? Question?
Yeah, I was wondering, is the electron flow or the proton flow?
Well, we call them positive charge carriers, right? Because if we call them protons, it's saying something really wrong, right? There's no positive charges flowing. We, again, for electrical current, which goes from higher voltage to lower voltage, we imagine it as positive charge carriers going to lower voltage. It's really electrons going to higher voltage. So that's why I say positive charge carriers, because they don't really exist. If I said protons, it would give it more reality than it actually has, right? So remember, that's the whole thing of electric current. We imagine it as the hypothetical flow of positive charge to lower voltage when it's really electrons flowing to higher voltage. Okay. Are there any other questions before I proceed? Okay, so we have this 12-volt drop from top to bottom. We know this is 12 volts. But they do not split it up 6 and 6. Okay, so that's one of the things we will discover, is that while in series current is the same, voltage is not. Okay, voltage is not the same in each resistor. And let me try to motivate for you why that is. Instead of two electrical obstructions, two resistors, okay, and instead of the flow of positive charge, let's replace positive charge with some kids and we'll place the resistors with obstructions that kids don't like. Okay, so we have a line of kids. We want to keep the line of kids moving smoothly. We want to bring them through two obstructions, kind of a smaller obstruction and a large obstruction. All right? The smaller obstruction is eating a piece of broccoli. Okay, kids don't like broccoli, right? Maybe some kids do, but for the purpose of the example, kids don't like broccoli. It's a minor obstruction for a kid to not eat a piece of broccoli. Second one, getting a shot. Okay, so getting vaccinated. Two things that kids don't like, but I think most kids would rather eat a piece of broccoli than get vaccinated, okay? So what do we need to do to keep this line of kids moving smoothly? We need to offer up, in exchange for these differing obstructions, we need to offer different rewards, okay? So here's the reward. You eat a piece of broccoli, we'll give you a lollipop, okay? Keeps it moving smoothly. We want you to get a shot, but then we'll take you to Disneyland, okay? We might be able to keep the line of kids moving slowly if we portion off the rewards according to the difficulties, right? And that's exactly what we do with the voltage drops, because remember, voltage drop is the reward. That's the energy reward for going from one end to the other. So what we're going to find is for the smaller resistor, we have a smaller voltage drop, and for the larger resistor, we have a larger voltage drop. That is the only way to keep this moving smoothly. Okay? So, let's figure it out. One thing we do know is that the drop from A to B and the drop from B to C in total has to add up to a 12-volt drop, right? So the entire journey from top to bottom is 12 volts. We know that the V1 and V2 have to add to 12 volts, but then we have to now be able to calculate, well, how much of each does it take? Because it's not just, they don't just split it in two. Well, let's just use Ohm's law. V1 equals I1R1. We can apply the Ohm's law to any individual resistor. So we already found out that there's 4 amps, and this is a 1 ohm obstruction. So we find that there's a 4 volt drop across resistor 1. And then we do it again with resistor 2, same thing. Same current, but now a bigger obstruction. We find there's an 8 volt drop there. And, wrapping things up very nicely, what do those two add up to? 12 volts, which we said, the entire journey from top to bottom, this entire height of this waterfall, this two-step waterfall from top to bottom, is 12 volts. So this is 12 volts. And we've just figured out that this step is 4 volts and this step is 8 volts. Okay? And the reason why one step is bigger, why the voltage drop of 1 is bigger, is because the resistor is bigger. More obstruction means more rewards to keep the thing moving smoothly. So we can not only say this is a larger resistor, and so it has a larger voltage drop, we can say because it's twice the resistance, it's twice the voltage drop. Right? The resistance was twice as big, 2 ohms versus 1 ohm. So was the voltage drop, 8 volts versus 4 volts. In fact, once you get really good at this, you can look at this and just write down the answers. You can just look at this and say, I know the voltage drop of this one has to be twice as much as this one, and I also need the numbers to add up to 12, because that's the whole drop. So sometimes if the numbers are round enough, you can just look at it. Oh, it's got to be, one number is twice the other, and they add up to 12. 4 and 8, right? So that's how it works. Voltage drop is not the same. The larger the resistor, the larger the voltage drop. The large resistances get the large voltage drops. And the larger the resistance is, the larger the voltage drop will be. I like to think of this as a bottleneck. Okay, so this is where the action is on a series chain. In a series chain, you have some big obstruction and some minor obstructions. Of course, the big obstruction is the big thing to worry about, right? That's the thing that needs to be paid the most attention, right? It's going to have the largest voltage drop of the entire chain. that make sense? So in this case, since this is twice as much, it has twice as much voltage. I think there's one homework problem where this is like 1 ohm and this is like 1,000 ohms. It's some ridiculous ratio, right? Which means that this is going to take 1,000 times the voltage drop of this, okay? So the small resistances start to not even matter. You have this one huge bottleneck that is the big show in town, okay? Are there any questions on that? Okay, so we found the voltage drops. Those are not equal. In a series, the current is. And finally, we move on to power, okay? So let's move on to power. Let me, again, copy these results up here. 4 volts, 8 volts. So I can save myself a little space to do the power. This is where we actually see why it's really nice to have 3 different forms of the power law. I'm going to suggest, and this is only a suggestion, it's not wrong if you do otherwise, I'm going to suggest this form for the series circuit, the I squared R. Here's why I suggest it. If you're trying to, say, solve for P1, the power dissipated by resistor 1, of course you'd use its current and its resistance. It's a lot harder to mess this up because I1, there's only one current, so there's no other currents to accidentally plug in, right? So I have 4 amps squared times 1 ohm, and I find that's 16 watts. Now, are the other ones wrong to use, the other forms of the power law? Absolutely not. I guess one example you could use is V1 squared over R1. Just be careful, because this is what students do all the time. They plug in V1 is 12 volts. Is V1 12 volts? No, it's 4 volts. So suddenly you have 1, 2, 3 different voltages, and you have to make sure to not accidentally plug in the wrong one. So that's fine if you are sure to plug in the voltage for that one alone, but you have things that are, it's easier to confuse it, so that's why I suggest the series one. It's this one for the series, because of course current is the same in series, and so you don't have to worry about it, right? There's nothing to accidentally plug in. There's no other currents that are even relevant or in the problem. Let's go ahead and do the other one. P2 equals I2 squared times R2. So again, can't mess up on the currents. Current's the same, but now the resistance is different. And I get 32 watts. Okay, so which one's going to be a little brighter then? The second one, that's right. Remember, power is our proxy for brightness. The amount of power dissipated, where does that energy go? It goes from electrical potential energy into heat and light. And if we're using light bulbs, you know, it's not just heat, but it's light as well. And we'll get more light release. We'll be able to see it with the naked eye. So the last box here, let me point out that when you're in a series, the larger resistances dissipate more power. So in a series circuit, we once again have the bottleneck situation. We have to pay the most mind to the big resistors. The big resistors is where all the action is. The bigger resistors, they take the most voltage drop, they take the most power, right? So the big resistors are the ones that matter the most, right? The more you have a giant resistor in there, the more it's going to hog the voltage drop, the more power it's going to dissipate. Question?
So in the single circuits, you had the larger resistance produces less power?
Correct. Yep. I'm actually going to compare it back to this in just a moment. That's why I left this here.
Okay.
So to finish the thought, of course, since I is the same, then this formula is really handy because we can see P equals I squared R. It tells us that the power dissipated is directly proportional to the resistance. So we can not only say that the larger resistance dissipates the more power, we can actually say that since one resistor is twice the other, it dissipates twice as much. So since this one is 2 times the resistance, it's twice the power. And that's what we found, of course, right? 32 watts versus 16 watts. Okay? So, let's now hook this thing up. And before I hook it up, let's make some predictions. Okay? We can compare the numbers to these to each other, and we can also compare these numbers to when they're connected individually. Okay? So let's make some predictions. I guess I'll try to sneak it in up here. So predictions. So the one thing that I can predict, of course, is that comparing the two, we expect that the larger resistor is brighter, right? So we expect that the larger resistor is brighter than the smaller one. Okay? The other thing that we notice, how do both of these values compare, the 16 and 32 watts, how do they compare to what they were when they were connected individually? So how does just greater or less, right? 16 watts, how does it compare to when it was connected alone? It's much less, right? 32 watts is much less than 144. Actually, I don't remember if, I think I might have crossed them by accident, but point being is that they're both much less in series than they were when connected alone. So while we expect that the larger resistor is brighter than the smaller one, we expect that both are not as bright as when connected alone. Okay. So the first statement, the first bullet point there is the relative brightness of the two to each other. And the second bullet point is how do they compare to when they're connected alone. Okay. So these are things that now we're talking about power, and we can just look at the bulb brightness and see if with the naked eye whether or not this is correct. You see what I'm going to do here? Okay, so let's try it. I'll go ahead and set up my circuit again. I showed you last time, we can do it again. So here are my two extending rods here. This just allows me to raise the thing so everyone can hopefully see it. Sorry if you need to get up, you're more than welcome to. I'm trying to accommodate both everyone in the room and make sure this shows up on the camera. So there's only so much I can do. Okay, so I've got the red attached over here. So this is going to be the higher voltage equipotential, right? This is going to be my region A. Over here, this is going to be my region C, my low. And I have to move these apart a little bit because I need to have room to hook up two resistors in series. So it looks like I have the small resistor first and the large resistor second. So this will be the stand-in, this will be my first resistor, and then this one will be twice as much. Okay, that's this 2R. You can't see that. So R and 2R, like that. So I'm going to connect them one after the other. I guess I should show you first, remind you since we did it last time, let me show you what they look like individually. So this is the brightness of this bulb individually, kind of try to take a mental snapshot. And then this one, try to take a mental snapshot of this one. Okay, like that. So that's how they look individually. That's these guys over here. Now let's connect them one after the other. So our prediction is that when we connect them one after the other, we have that in our predictions in that box over there. So let me hook it up. Whoops, wrong one. So here's our series. So we have equipotential region A over here, that's the highest voltage, leads right up to the bulb right here. We have a region C over here, that's off here, and then we do have a middle region here as well. This is step B. So we have, you can go from A to B, and from B to C, okay? So let's turn it on. First of all, are they both glowing? Not as bright as when connected alone. Hopefully you can see that's the case. Also, we do see that out of these two, the larger resistor is brighter, right? This is our bottleneck over here, right? So this is where most of the action is happening. Most of the voltage drop, most of the power dissipated is in the larger resistor. Does that make sense? Any questions on this? Okay, so that is the series circuit. We're ready to move on to the parallel. Take this down so it doesn't block the board. So let's clear some space and do the parallel. Same ingredients, same 12-volt battery, and then we'll have two resistors, but we'll connect them in the same two resistors, connect them in a different way. Here's our 1 ohm, and here's our 2 ohm. It's like this. So, same thing, we're going to go through and we're going to figure out what are our plateaus. So let's do it. Here's the high voltage terminal of the battery, and any contiguous piece of wire connected to it just extends that plateau. I'll call that region A. And then my lower voltage plateau, and any contiguous piece of ideal conductor connected to it just extends that. And I'm going to call that region B because that's it. That's all there is to it. There isn't a middle step anymore because of the way I connected the resistors. There's no space tucked away between the resistors that isn't connected to either battery terminal. Now all we have are two different ways to get from the top to the bottom, from A to B. We have two different options. That's what makes this a parallel circuit, is that you have the option to go one way or the other way, but you'll never do both. If a positive charge wants to get from higher voltage to lower voltage, it picks one of these options. It's never going to go through this and then just go back up through this, because it's just going back where it just came from, right? So in the parallel, voltage is the same. Each resistor presents the exact same voltage jump from the same region to the same other region. It's just different options to do it. So the voltage is the same. Okay? The voltage drop across each element is the same. You're giving multiple options between the same two places. If we were going to draw the voltage waterfall, the voltage waterfall would look like this. You simply have two different options. to go between equipotential plateau A and B. Okay? So having multiple options, though, does not mean that all the options are, of course, equally easy. So as far as the current goes, the current will not be the same. The current is not the same in each resistor. You can probably guess which way does more current go. The smaller resistor. It's easier, right? More current will go through the small resistor, the easier obstruction, and less will go through the hard way. So here, if the resistance is lower, the current will be higher. This makes sense, right? You have parallel options to get home, right? Maybe you could take the highway, maybe you could take local roads, right? Let's assume that the highway isn't jammed up. It's probably the easiest way, right? So that would be like the path of least resistance, as they say. You might question, why would anybody go through the hard way? Okay? Well, if you see everybody's heading toward the highway, you might think, is no one out on the local roads? Maybe I'll take those. Some people do that every day. Not as many, but some, right? The way I like to think of it is, another way to think of it is like toll booths on the Bay Bridge, okay? You have toll booths, right? All in parallel. If you somehow manage to go through 2 toll booths on your way across to the city, you've really done something illegal, okay? You pick one of them to go through, right? So the easy way might be someone who, makes change really fast. But even if you have someone who makes change really slowly, that's like a big obstruction, you'd still probably rather be first in line there instead of being 15th in line over here, right? It still makes sense for some charges to go through the hard way, just not as many, okay? So let's calculate. I1 equals V1 over R1, okay? I'm using Ohm's law. I know that the voltage drop across both of these is the same, and it's just the battery EMF, it's 12 volts. So I'll just put that in, 12 volts over a 1 ohm obstruction, that's 12 amps. And I2 is V2 over R2, same motivation, more resistance, 6 amps. So we've confirmed with calculation what our intuition already told us, is that less current goes through the hard way and more current goes through the easy way. In fact, we can say this. Because this resistor is twice as much, it gets half the current. It gets half as much current as the other one. So I like to think of it as these big resistors, when you're in series, they're the bottlenecks, because you have to go through everything, and the big ones, you have to pay them the most attention, right? Whereas, in this case, if you have a big resistor, but you have easier options, of course, the big resistors end up being the sideshow, right? More goes through the easy way. So I guess let me put here that now the big resistors are the sideshow. And I guess I need to reverse this. If I'm talking about the big resistors get less current, okay? So I'm kind of referring to the big resistors. Big resistors are the bottlenecks in a series, and they're kind of the sideshow on the parallel, okay? All right. Are there any questions before I move on to the next couple rows on that chart? Okay, so I guess let's talk about resistance. So if we have, I guess we discovered that there's 12 amps going from here to here, and there's 6 amps flowing from here to here. This is like a river with forks, right? So we found that as this river of charge splits off into two forks, we found that one fork gets 12 amps and one gets 6. So how much total current must be supplying these two branches? 18, right? So I total is sourcing I1 and I2. And so I total must be, of course, 18 amps, which is way, way, way bigger, okay? Notice that 18 amps is way bigger than when they were connected alone. And so if you're having this much current, this huge rush of current, what does that mean about the entire resistance of the circuit? Is it high or is it low? It's very low, okay? So that turns out that if I total is really high, then the equivalent resistance of the entire circuit is low. So let's think about how that could be. How is it that when you place these two resistors like this, it presents so little impediment to electrical flow? Well, think about it like this. Let's say we had that 1 ohm restriction, and that's all we had. Everybody would have to go through that way. That's like when only one toll booth is open, right? You can add a second lane. It's always better to have a second lane open no matter what, right? No matter how obstructive it is, it's still better to have it there than not, right? So when we took our 1 ohm and we added another branch, that still made it easier to go through. It brought down the total resistance, right? It's still better to have an extra lane. That's why all of the toll booths are hopefully open during rush hour, because it's always better to have more. If we added a third branch here that was at a resistance of 1,000,000 ohms, it's still better to have it there than not, because it gives an extra option. Every single resistor that you add in parallel actually brings the resistance down. It's still adding extra options. And that's even if these extra branches have a incredibly high resistance, it's still better to have the option for a few charges to go over there, right? Does that make sense? So what we're going to find is that the equivalent resistance of a parallel circuit is actually lower than any individual member. Adding resistors in parallel actually decreases the resistance. So how am I going to figure out the exact formula? Let me go ahead and just use this. Let me use this idea that the total current sources every branch. So if you remember, I can kind of think of the circuit as having some total or equivalent resistance, and that total or equivalent resistance is going to set the current, right? I total is going to be set by the battery and the total resistance or equivalent resistance that is presented. So let me go ahead and plug that in. I total is equal to EMF over R equivalent. And let me go ahead and also sub in I1 is V1 over R1, and V2 is, or I2 is V2 over R2. So basically using Ohm's law 3 times. Twice for the individual resistors, and then once for the circuit as a whole. Now let me remind you, all these voltages are one and the same. So we have actually just discovered what is the rule for adding resistors in parallel. It's a 1 over rule. 1 over R equivalent is equal to 1 over R1 plus 1 over R2. And hopefully you remember your math, that you can't just flip everything into the numerators. It doesn't work like that. Okay? So it's a 1 over rule. So we go back over here to our chart. This is the rule for figuring out the R equivalent. Is actually to sum the reciprocals of the resistances, and you will get the reciprocal of the equivalent. Right? Let's try it out and see that it works. So 1 over R equivalent should be 1 over 1 ohm plus 1 over 2 ohm. So we get 1 plus 1 half. 1 plus 1 half is 3 halves, right? And yes, it might look odd that the ohms is in the denominator. If you want, just ignore it. In fact, let's not write it with the resistors. Looks like that. Now here's a common mistake. You look at that, the 3 halves are 1.5. That is not adhering to the claim, of course, that the resistance overall is below any of the individual ones. I have a 1 ohm and a 2 ohm and 1.5 in between them. Of course, the mistake is that I haven't yet flipped it. Remember, this is 1 over R equivalent. So that's why the ohms was in the denominator, is because, of course, I need to flip it. The equivalent resistance of this whole circuit is actually 2/3 ohms, which is, as advertised, is less than any individual member. So when you're doing this in your calculator, remember, 1 reciprocal, 2 reciprocal, add them, take the reciprocal of the result. Okay, don't forget that last step. Okay? So the equivalent resistance presented by this is 2/3 ohms. And we can now go ahead and plug it in and make sure that it works. I total equals EMF over R equivalent. We have a 12-volt journey from top to bottom, and 2/3 ohms of resistance, very little resistance in the way, and 12 over 2/3 comes out to be 18 amps, which is what we found, right? So it works. An incredibly large amount of total current because you have multiple lanes open, and so you have lots of different options, okay? Are there any questions before I move on to the power part? Yeah?
So would you say 1 over R equivalent
Yep.
is equal to 1 over R average?
But what average?
The average of total.
No. It's 1 over each individual resistor. 1 over 1 ohm, 1 over 2 ohm.
Okay.
That is not something that you can try it out with different things. If you see some kind of other connection, it's pure coincidence, okay?
Okay.
The 1 over rule is what you want to use. Question?
This might have been the same thing he was asking. Could you, if you were not given the individual resistances, but you're given the amps and the voltage, could you use Ohm's law to find the circuit resistance?
If you're given, given what?
Just the amperage and the voltage, not the individual.
So you're given the total current, okay, and
voltage.
of the battery?
Yeah, could you use Ohm's law just to find the resistance of the whole circuit?
Yes, absolutely. I mean, those two are right here. All you need to find the total current is the battery voltage and the equivalent resistance.
So that's what you did there.
Yeah.
Okay.
Yeah, I mean, that doesn't necessarily tell you how that equivalent resistance comes to be, right? There's all sorts of different networks of resistance that coincidentally happen to have the same resistance, right? But this particular network of resistances, a 1 ohm in parallel with a 2 ohm, happens to result in an equivalent resistance of 2/3 ohms. And now that that is established, the charge carriers sense how much total resistance is in there, and they will flow accordingly. So there'll be 18 amps that flows, and then 12 amps will splice over this way, the easy way, and 6 amps will go over here. Any other questions before I move on to power? Okay, so let's do that. Oh, and I forgot to mention too, one of the things of this 1 over rule, if you say have a bunch of identical resistors, so let's say you have a bunch of identical resistors of value R, well you're going to have, if you have let's say 10 resistors, you'll have 10 of these. If you have 2 of these, you'll just have 2 of these terms. In general, if you have n of those terms, right, for n resistors. So you can then flip this and find an interesting rule, is that when you have a bunch of identical resistors in parallel, you divide by the number you have. So that's, we can add it over here. R equivalent is R divided by N, okay? So it's a nice shortcut so that you don't have to do the 1 over rule, especially if you have a bunch of resistors that are all identical and they're all in parallel, all in series. You can just very quickly get the answer. I'm trying to give you a few shortcuts. So for instance, if you had a bunch of resistors, all that had 10 ohms, and let's say you had 5 of them, okay? So you have, someone gives you a box of resistors. They're all 10 ohm resistors. There's 5 in the box. If you put them in series, what would be the equivalent resistance? If you put 10 or 5 resistors in a row, all of 10 ohms, what would be the equivalent resistance? 50 ohms if you put them in a row. But if you put a parallel situation where you had all of 5 of your resistors as parallel branches, different options, what would be the equivalent resistance of that? 2 ohms. So you can see that you have, even though you only have a box of 10 ohm resistors, you have a wide variety of latitude in terms of how much total resistance you can get. And perhaps intuitively, you can create a resistor that's much smaller overall than any one if you put them in parallel. So you can see there's a lot of similarities here, and that's why I'm kind of course, putting the series and parallel side by side so you can see this. Okay, so let's move on to the power. Let's clear some space over here. So again, this is where I have the opportunity to show you why it's nice to have several forms of the power law. I'm going to suggest this one for parallel. Why this one? Well, it's hard to go wrong. It's got a V in there, and of course V is the same for every resistor in the parallel chain. So there's no wrong V to plug in, right? So let me do P1 equals V1 squared over R1. It's really hard to go wrong when you only have one voltage. You just put in that voltage, 12 volts, and divide by the square it and divide by the resistance. You get 144 watts. And are the other ones wrong? No, they're not wrong. Can you use I1 squared times R1? Sure. Which current do you plug in? 12 amps, 6 amps, or 18? If you get it right, you get the right answer, but there are 3 different currents, the total current and then the 2 branched currents. Which one is it? It's 12. Okay? It's not that it's wrong, it's just easier to mess up. So that's why I suggest this one. There's no other voltage to confuse. So let's do the same thing with resistor 2. So what we have, hard to mess up on the voltage, same thing, but now just dividing by the resistance, we get 72. So there's our power dissipated. You can see hopefully why I came up with these 2 forms of the power law, because if I just went with the original instead of substituting Ohm's law in selectively, I couldn't have developed these ones that are really nice for series and parallel. Okay? So these alternate forms of the power law. It's not that the other ones are wrong, it's just hard to mess up, or it's easy to mess up. All right, so we have gotten the power. Which resistor is brighter? Which one is brighter, P1 or P2? P1. Now it's the smaller one that's brighter. That's where all the action is, right? fact, here, since V is fixed, we see that P is proportional to 1 over R by this equation. Okay? Okay, so since the V is the same, you can see I plugged in the same value, we find that the power goes inversely as the resistance instead of directly proportional to it. So what we find is that the smaller, or the larger resistors now dissipate less power. And this goes right along with my idea of the sideshow, okay? So when you have a series circuit, the big resistor is where all the action is, right? The most voltage, the most power. But those same big resistors now, when the charges have other options, become the stuff where there's not as much happening. So the large resistors now get less current and less power, okay? Now, let's do the same thing. Let's make some predictions and hook it up and see if that's the case. All right? So, let me save my box here. Predictions. Try to carve out a little space. Okay. So first, we'll compare the two to each other. So we said now, which resistor should this be brighter? The larger resistor or the small resistor? The small one. So now, the smaller resistor should be brighter than the other one. So that's a relative comparison of the two to each other. And then, of course, the other comparison that we made was, how do these compare in themselves to what they did individually? So how do these two numbers compare to individually? They're the same. Both of them should have the same brightness as when connected alone. So those are our two predictions. All right, let's hook it up and we'll see if that's the case. So go ahead and we'll put down our two extenders here for our equipotentials. We'll hook up our voltage source. Let's bring in back in our resistors. So here's R connected alone. And now I have, so this is my region A, my equipotential region A, my higher one. This is my lower one. Okay? And now I'm going to give an extra option to get from the higher to the lower, right? So we'll bring in my other resistor. So watch the brightness of this one when I connect this, and we'll see if that changes at all. Okay, our prediction is that something should have the same brightness as when connected alone as when it's connected with other things in a parallel. So we'll throw this in here, and this one should not change at all. Did it change? It's changing, right? Okay. This is our first chance to actually compare them side by side. And our prediction was that the smaller resistor should be the brighter one. This is slightly more blinding. Hopefully you can see that, at least in person. Here, most of the glass is hard to see. This, you can see more of the glass. I know it's subtle, okay? So, but trust me that this one, because it's a larger resistance, dissipates less power. And hopefully we're convinced by this second one is that it's the same brightness when connected alone. So let me remark on how can it be the same brightness, okay? How can it be the same brightness connected alone as when connected with the other ones. We've just went through this big fuss and about this idea of equivalent resistance. When we connect these branches up, we are giving further options for the charge, right? So further options means the total resistance goes way down and the total current goes way up. But here's the thing. I might have an extremely large amount of current right now being sourced here that's splitting off into both of these. But that larger current also has more mouths to feed, right? It now has to splice off into two branches as well. I can add a third resistor. I gotta be really careful here, because that's a third mouth to feed, okay? So if I add a third resistor, it brings the equivalent resistance even more down and the total current even more up. Okay, so the total current here is going to be very, very large. But notice that the other two bulbs don't care, okay? That is, by the way, why I'm using a car charger, because this thing can source up to 350 amps, okay? It's never going to be taxed. Any current I asked of it is basically going to be available, okay? In your lab, I'll tell you right now, we're not going to give you something that can source an arbitrarily large amount of current. So you might actually see, when you start to add 3, 4, 5 branches, you might see them all dim. That's just simply because this thing is failing to do its job, right? So that's why I'm using this, is because we see ideal behavior. If I add a bunch of these resistors, the total current requested is immense, but it slices off into each branch, and each branch gets exactly the same amount of current if it's connected alone or if it's connected with a bunch of other things, right? We found that the current 6 amps, basically each branch has this request. Each branch requests a certain amount of current, and it's supplied, and the total current is just larger because it has more mouths to feed, okay? If you look at the equation, for any individual resistor, let's say V1 equals I1R1, the resistance, of course, is the same. The resistance of an individual resistor doesn't change. And these are all different options also to go across the same voltage drop. So whether you have 1, 2, or 12 branches, it's a 12-volt drop. And so what we're forced to conclude is that the amount of current flowing through each one is the same, whether it's connected alone or if it's connected with a bunch of other things. And that's, of course, if you know the meaning of the word parallel, it means independent, right? It means things are happening truly independently. Each bulb has the same current going through it and the same voltage drop, whether it's connected alone or connected with a bunch of other things. Of course, it's up to the total current to decrease or increase as it has more or less mouths to feed, right? So I'm not saying that the total current is the same. So the resistance of the circuit overall goes down with every branch added. The total current goes way up. But that total current is just split off into more branches. Each individual branch has the same current as it did before. And that leads to the fact that it also has the same brightness. Okay? Did you have a question?
I think you answered it.
Okay. Anyone else have any questions? So this is, of course, an advantage for the parallel, right? Is the fact that each branch is independent. If you disconnect or reconnect a branch, the other ones don't care at all, okay? So at this point, we've kind of finished our discussion about pure parallel and pure series circuits. Then one of the next things we will do, probably won't have time for much today, but we'll do some conceptual stuff. We'll kind of hook stuff up and just kind of conceptually work through what happens. And we'll also do what are called combo circuits. So combo circuits are ones that have both series and parallel elements. We can connect the resistors in a kind of strange ways that it's not only series or only parallel. Okay? So an example, for instance, would be, what if I hook these two up in parallel, like this, but then I made all the charge converge in series to go before it went over here. So I think that's the combo circuit you guys will hook up in lab next week. So you have two resistors in parallel, go in series with a third. Okay? So we'll talk about combo circuits. That's just a little bit of a preview where we're going with this. I guess in the next few minutes, let me just say a few very practical usages of the series and parallel. For instance, Christmas lights, right? String of lights. They look like they're in a series, but they're not. Okay. Things, how they look cosmetically and what they actually are can be very different. I think one of the things that people get obsessed about in parallel circuits is actually physically being parallel. This isn't parallel, okay? They're not literally train tracks, okay? You have to get over that. You'll pull your hair out trying to hook up circuits if you don't understand why this is parallel, okay? Look at it, right? There's the top voltage region. There's the bottom voltage region, and you have option 1 and option 2, okay? So they don't literally have to be train tracks parallel. Similarly with Christmas lights, they might look parallel, but here's what actually happens with Christmas lights. They might look like they're all in a row, but guess what? They're all independent paths from the beginning to the end, okay? Because if one bulb burns out, the last thing you want is for everything to go out, right? If you truly had, these were like this, if bulb burns out, then there's no viable path, so they all go out. The reason Christmas lights look like the way they do is they used to be in series. And then when one bulb burned out, they all went out because there's no way through anymore. And you took out your replacement bulb and you very patiently unscrewed every bulb and tried the replacement until you found the one that went out. God forbid 2 went out at the same time. Then you're there for ages, okay? Christmas lights, they might look like they're all in a row, but every single bulb has an independent path from top to bottom. And so if one burns out, then the rest stay on. You just look for the one that's burnt out and you replace it, okay? This is, of course, a thing where parallel has an advantage. So parallel has an advantage. We make them look like they're in a row, but they're really not. They're all independent paths from top to bottom. And series, you did not want to do it, okay? So there's an example, Christmas lights, where parallel is a good thing. Next time we'll start off and looking for when something like this, the fact that one burns out and kills the path from beginning to end, where that's not a flaw, that's a feature. So there are times where that's good. So we'll find that both series and parallel have their place in terms of very useful electrical functions. So let's knock it off there for today.